Hello students, I welcome you to the digital lecture series Bajaj College of Science, Varda. I am Dr. Mrs. Neeta Mohansi, Assistant Professor, Department of Chemistry, going to discuss on the topic Chemical Kinetics. Contents of my today's lecture are definition of chemical kinetics, rate of chemical reaction, factors affecting the reaction rate, molecularity of reaction, order of reaction, pseudo-unimolecular reaction, zero-order reactions. Chemical kinetics. It is that branch of physical chemistry which deals with the study of rates of chemical reaction and various factors influencing the rate. Depending upon the speeds of chemical reactions are classified as fast or instantaneous reactions, extremely slow reactions, moderate reactions. Fast or instantaneous reactions are those reactions which occur at very high speed. Hence, these reactions cannot be studied. For example, neutralization of strong acid by strong base, many other ionic reactions. Second one are extremely slow reactions. As name indicates, these reactions take long time to complete. For example, rusting of iron, combination of H2 and O2 at ordinary temperature. Third and most important one are moderate reactions. These reactions take place at measurable speed. For example, inversion of cane sugar, hydrolysis of methyl acetate, etc. One of the important terminology in chemical kinetics is the rate of chemical reaction. Rate of chemical reaction is defined as the change in concentration of any one of the reactant or product per unit time. For example, decomposition of hydrogen peroxide. Hydrogen peroxide on decomposition gives H2O and oxygen. The rate of this reaction can be written as either the change in concentration of reactant per unit time or change in the concentration of the product per unit time. It is shown by these two equations. In first equation, rate of reaction is equal to amount of reactant H2O2 consumed per unit time, or rate of reaction is equal to amount of O2 produced per unit time. General unit of reaction rate for nth order reaction is dm cube raised to power n minus 1 mole raised to power 1 minus n second inverse. Variation of reaction rate and concentration with time. Consider a general chemical reaction A gives B. When a graph is plotted between concentration versus time, it is observed that the concentration of reactant A decreases with time, while the concentration of the product increases with time. Now, various factors influencing the reaction rate are nature of reacting species, temperature, concentration of reactants, pressure, presence of catalyst, effect of radiation, surface area of reactants. We are going to discuss these factors one by one. First factor is the nature of reacting species. Chemical reaction is defined as the breaking of old bonds and the formation of new bond. every bond has its definite bond energy. With the change of reactants into products, bond energies goes on changing. The ease with which old bonds are broken and new bonds are formed determines the rate of chemical reaction. Consider these two reactions. These two reactions look similar, but first one is fast while second one is slow, because the bond between N and O in the first reaction are easily broken as compared to the bond between C and O in second reaction. The second and the most important factor that influences the rate of chemical reaction is the temperature. Rate of reaction is directly proportional to temperature. Means, as the temperature increases, the rate of chemical reaction increases and vice versa. In most of the reactions, the rate of reaction almost gets doubled with every 10 degrees Celsius rise in temperature. This is due to the fact that with the increase of temperature, kinetic energy of the molecules increases. As the kinetic energy of the molecules increases, the number of effective collision increases and thus the rate of chemical reaction increases. Third factor, concentration of reactants. The rate of reaction is directly proportional to the concentration of reactants. When concentration of reactant molecules are high, the probability of their interactions is also high and thus the rate of reaction increases. For example, consider the burning of wood. Burning of wood is rapid in pure oxygen than in air, because the air contains only 20% of oxygen. Next factor is pressure. In gaseous reactions, with increase in pressure, the rate of reaction increases. With increase in pressure, the reactant molecules come closer and so the probability of effective collisions also increases. Thus, the rate of chemical reaction increases. Presence of catalyst. Catalyst is a substance which by its mere presence increases the rate of chemical reaction without undergoing any chemical change. Presence of catalyst increases the rate of chemical reaction. For example, hydrogen and oxygen react with each other only in presence of finely divided platinum as a catalyst. Effect of radiations. In some chemical reactions, the bond energy of reactants are such that they are broken by the radiations only. Thus, the rate of reactions depend on the intensity of the radiations. For example, the photochemical combination of H2 and Cl2 takes place in presence of sunlight. Surface area of reactants. In heterogeneous reactions, one of the reactant is in solid state. In these reactions, the rate of reaction increases with the increase in the surface area of reactants. More the surface area, more the chances of the interactions of the reactant molecules. Solid in the form of powder will have higher surface area than to a single block. Now, another important terminology in chemical kinetics is the molecularity of the reaction. Total number of molecules that are taking part in chemical reaction is called as molecularity of reaction. Depending upon the number of molecules that are taking part in chemical reactions, chemical reactions are classified as unimolecular reactions, biomolecular reactions, termolecular reactions, or these are also known as trimolecular reactions. Unimolecular reactions are those reactions in which only one reactant molecule is participating. Bimolecular reactions are those reactions in which two molecules are taking part in the chemical reaction, while termolecular reactions are those reactions in which three molecules of the reactants are taking part in the chemical reactions. Consider these examples. In first example, only one molecule of N2O5 is taking part in chemical reaction and hence it is unimolecular reaction. While in second reaction, one molecule of H2 and one molecule of I2 is taking part in chemical reaction and hence it is a bimolecular reaction. In third reaction, two molecule of NO and one molecule of O2 is taking part and hence 2 plus 1 it is a trimolecular reaction. Order of reaction. Order of reaction is defined as the number of reacting molecules whose concentration changes appreciably as a result of chemical reaction, or it is also defined as the sum of the powers to which the concentration terms of the reactants appearing in the rate law expression. Consider the general chemical reaction. M moles of A react with N moles of B gives you product. For this reaction, rate is equal to K into concentration of A raised to power M into concentration of B raised to power N, and thus order of the reaction is equal to M plus N. Consider these three rate equations. In first rate equation, R is equal to K into concentration of A. Hence, it is a first order reaction. In second rate equation, rate is equal to K into concentration of A raised to power 1, concentration of B raised to power 1, and thus 1 plus 1 it is a second order reaction. While in third rate equation, rate is equal to K into concentration of A raised to power 2 into concentration of B raised to power 1, and thus 2 plus 1 it is a termolecular reaction. Consider these two examples. First one is the saponification of ethyl acetate. In this reaction, one molecule of ethyl acetate and one molecule of NaOH is taking part in the reaction, and hence the molecularity of this reaction is 2. At the same time, the rate of this equation depends upon the concentration of ethyl acetate molecule as well as the NaOH molecules, and thus order of this reaction is 2. While in second chemical reaction, molecularity of reaction is 2, but order of reaction is 1 because the rate of the reaction depends only on the concentration of methyl acetate molecules. Pseudo-unimolecular reactions. Pseudo means false. The reaction which is not truly unimolecular but its order is 1 is known as pseudo-unimolecular reactions. Consider these examples of pseudo-unimolecular reactions. Hydrolysis of methyl acetate in presence of an acid. In these reactions, the rate of reaction depends upon the concentration of only methyl acetate molecules. Since water molecule is taken in large excess, there is no considerable change in its concentration, and hence the rate of reaction depends only upon the concentration of methyl acetate molecule. Thus, for this reaction, although the molecularity of reaction is 2, but order is 1, and hence it is also known as pseudo-unimolecular reaction. Other examples of pseudo-unimolecular reactions are inversion of cane sugar, hydrolysis of an organic acid, organic chloride, zero order reactions. The reaction in which the rate is independent of concentration of all the reactants is called as zero order reaction. Examples of zero order reactions are decomposition of ammonia in presence of nickel gives nitrogen and hydrogen. Second, decomposition of HI in presence of gold as a catalyst. And third one is the photochemical combination of H2 and Cl2 to give twice HCl. Now we are going to derive the rate equation for the zero order reaction. Consider the reaction A gives product. Let the initial concentration of the reactant is A mole per liter. Suppose at time t, x mole per liter amount of A changed into products. Rate equation for this reaction can be written as rate is equal to K into concentration of A, and that is equal to small k, that is dx by dt, that is the rate of formation of the product with time, is equal to k. Simplifying, dx is equal to k dt. On integrating both sides, we get integration dx is equal to integration k dt. On integrating this equation, we get x is equal to kt plus c, where c is the concentration of the constant of the integration, and it can be calculated by using the initial conditions. When t is equal to 0, the amount of reacted, that is x, is equal to 0, and thus equation 3 gives c is equal to 0. Substituting c is equal to 0, equation 3 becomes x is equal to kt. This is the rate equation for the zero order reaction. Characteristic of the zero order reactions are units of the rate constant for the zero order reaction. The rate equation for zero order reaction is given by K is equal to xt. The unit of concentration is mole per liter, and the general unit of time is time, and hence the unit of rate constant is mole per liter per unit time. Graphical representation of the zero order reaction as the rate equation for the zero order reaction is x is equal to kt. This is the equation of the straight line of the type y is equal to mx. Thus, when a graph is plotted between x versus time, a straight line passing through origin is obtained. The slope of this line will give you the value of the slope k. But when the graph is plotted between the rate versus concentration, it was found that the rate is independent of the concentration of the reactant and gives a straight line parallel to the x-axis. That's all from the topic chemical kinetics. For more lectures and information, please visit college website. Thank you.